Imagine you're trying to translate a sentence. Previously, models would process words one by one, remembering what came before. It was a bit like reading a book out loud, word by word.
Right, like a chain, where each link depends on the one before it. That's how we typically think of sequence models.
Exactly. But what if you could look at all the words simultaneously, understand their relationships, and then translate? That's the ambition behind the transformer. The Attention is All You Need paper, which first introduced the transformer, directly addressed limitations of existing models for sequence tasks like translation.
So it was about finding a better way to handle dependencies in a sequence, but without the sequential processing bottleneck?
Precisely. The abstract states, the dominant sequence transduction models are based on complex recurrent or convolutional neural networks. The authors proposed a radical shift, creating a new simple network architecture, the transformer, based solely on attention mechanisms.
Solely on attention? That seems like a strong claim. What did they remove to achieve that?
They were dispensing with recurrence and convolutions entirely. No more sequential RNNs or local CNN filters for context.
We've touched on self-attention before in case tag TCM123001. So the transformer took that core idea and just scaled it up, replacing everything else?
That's a great way to put it. They showed that attention isn't just an add-on for a recurrent model, it can be the model's fundamental building block.
And that's what makes it so groundbreaking, the confidence that attention is sufficient.
This architectural choice wasn't just elegant, it had massive practical benefits. The paper highlights, experiments on two machine translation tasks show these models to be superior in quality.
Superior quality is always the goal, of course, but what about the how behind that improvement?
The key was parallelization. This attention-only structure made the models more parallelizable and requiring significantly less time to train.
Wait, less time to train because of parallelization? How does replacing recurrence with attention make it inherently more parallel?
With recurrence, you compute one step, then the next. You have to wait. But attention can calculate dependencies between all pairs of words at once.
So the entire input sequence can be processed simultaneously, not sequentially? That's a huge shift in computation.
The results were striking. For English to German, their model achieves 28.4 BLUE, improving over the existing best results.
Over 2 BLU points is a significant leap in machine translation. It really validated their architectural decision.
Indeed, for English to French, it established a new single-model state-of-the-art BLUE score of 41.8.
This must have been a moment where the field realized something fundamental had changed, like the future of sequence modeling looks different now.
Absolutely. The transformer quickly became foundational, not just for translation, but for many sequence tasks, even generalizing to English constituency parsing.
And eventually to other modalities, as we explored in case number TCM063005 on vision transformers.
So the transformer showed us that attention is powerful enough to stand alone. But how does this attention-only architecture actually work?
That's what I'm wondering. What does attention is all you need look like in practice? Let's open up this black box.
Next, we'll dive into the intuitive components of this architecture, moving from the high-level design to the specifics of how self-attention processes information. To understand the transformer, let's start with a high-level picture. The illustrated transformer describes it as a single black box for machine translation.
Like an input-output machine. You put a French sentence in, and an English sentence comes out.
Exactly. But if we, popping open that Optimus Prime goodness, we see two main components, an encoding component and a decoding component.
So an encoder processes the input sentence, and a decoder generates the output sentence, just like traditional sequence-to-sequence models?
Yes, conceptually similar. The encoder takes the source language, and the decoder generates the target. Each of these components is actually a stack of encoders or a stack of decoders.
So it's not just one encoder, but several stacked on top of each other. That adds depth.
Let's focus on one encoder. The author explains it has two sublayers. First, the encoder's inputs first flow through a self-attention layer.
Self-attention. So this is where the magic happens, learning relationships within the input sequence itself.
That's right. It helps the encoder look at other words in the input sentence as it encodes a specific word. After self-attention, the output then flows to the second sublayer, a feed-forward neural network. This network processes each position independently.
So self-attention computes relationships, and then a standard feed-forward network transforms those context-aware representations?
Precisely. And importantly, the exact same feed-forward network is independently applied to each position.
This independent application of the feed-forward network, does that mean it loses all the context self-attention just built?
That's a good question and a common pitfall. No, the context from self-attention is baked into the vector before it hits the feed-forward network.
So the feed-forward network is just refining the already contextualized representation at each position.
Now, a crucial property for parallelization. The word in each position flows through its own path in the encoder.
So each word, once embedded, can go through its encoder layers without waiting for other words, except for that self-attention step?
Exactly. The feed-forward layer does not have those dependencies, meaning those parts can be fully parallelized. The self-attention layer is where the paths interact. Think of self-attention using a classic example. The animal didn't cross the street because it was too tired.
What does it refer to here? The animal or the street? Humans get it instantly, but for a model, that's ambiguous.
Right. Self-attention allows the model, when processing it, to associate it with animal. It explicitly looks for clues in the sentence. The author clarifies the role as the model processes each word. Self-attention allows it to look at other positions in the input sequence.
So it's constantly gathering relevant information from the entire context for every single word it processes.
Yes, it helps bake the understanding of other relevant words into the one we're currently processing.
I see the high-level structure now and the goal of self-attention, but how does it actually look at other words and bake understanding?
That's where the query, key, and value vectors come in. Next, we'll unpack the precise mechanics of self-attention step by step. Let's delve into self-attention in detail. The first step for each input word is to create three vectors: a query vector, a key vector, and a value vector.
So every word gets its own Q, K, and V. What are these based on?
They are created by multiplying the embedding by three matrices that we trained during the training process. These matrices project the word embedding into different spaces.
Query, key, value. Those sound like database terms. Is there an analogy there?
Absolutely. Think of it like searching. Your query is what you're looking for. Keys are like the tags on documents. Values are the documents themselves.
So the query of one word is used to find relevant information from the keys of all other words?
The second step is to calculate a score.
This score measures how relevant other words are to the current word we're processing.
How is that relevance calculated mathematically?
The score is calculated by taking the dot product of the query vector with the key vector of the respective word. A higher dot product means higher similarity.
If we're calculating attention for thinking, we take Q1 and K1 for its self-score, then Q1 and K2 for its score with about, and so on for every word.
So the query of thinking interacts with the key of every word in the sentence, including itself.
Yes, that's what makes it self-attention. Every word attends to every other word in the sequence, symmetrically.
Next, the third and fourth steps are to divide the scores by 8, then pass the result through a softmax operation.
Why divide by 8, and what does softmax achieve here?
The division helps with stable gradients during training. Softmax normalizes the scores so they're all positive and add up to 1, turning them into attention weights.
So, after softmax, we have a set of weights telling us how much to pay attention to each word for the current position.
Exactly. This softmax score determines how much each word will be expressed at this position. It's an interpolation coefficient.
And since it adds to 1, it's like distributing a fixed amount of attention across the whole input.
The fifth step is to multiply each value vector by the softmax score. This weights the information of each word by its calculated importance.
So the high-scoring words contribute more of their actual content, while low-scoring words fade into the background?
That's precisely the intuition. It's to keep intact the values of the words we want to focus on and drown out irrelevant words. Finally, the sixth step is to sum up the weighted value vectors. This aggregation produces the final output of the self-attention layer for that position.
So the output for a single word is a blend of all value vectors weighted by how much each key matched the query.
Yes, it's a context-aware representation that has baked in information from the entire sequence. This concludes the self-attention calculation.
This all happens in parallel for every word, right? So the output for each word is computed simultaneously?
Yes, crucial point. That's the power. But remember, words still need positional encoding for order, since attention itself doesn't inherently understand sequence order. This is where the analogy to a bag of words breaks.
We've seen how the transformer self-attention mechanizes context. Now, how did this fundamental architectural shift lead to models like BERT transforming NLP?
So from this core mechanism, how do you build something that achieves state-of-the-art understanding across many language tasks?
The transformer's ability to process sequences with deep, parallelizable attention layers laid the groundwork for models like BERT.
We touched on BERT's evolution in case TCM 153002. Today we can really see why the transformer was so key to its success.
Exactly. BERT leveraged the transformer's encoder stack to create powerful language representations. The BERT paper introduces a new language representation model called BERT, which stands for Bidirectional Encoder Representations from Transformers.
Bidirectional encoder representations from transformers. That name itself tells you a lot about its core design.
It certainly does. It signals its deep connection to the transformer architecture we just explored. Unlike previous language models, BERT was designed to pre-train deep bidirectional representations from unlabeled text.
Bidirectional here means it considers both left and right context simultaneously for every word, right? Not just left to right like traditional LMs.
Precisely. It does this by jointly conditioning on both left and right context in all layers. This is a fundamental advantage of the transformer's attention.
But how can it see both left and right context without cheating during pre-training, like seeing the word it's supposed to predict?
That's a key design choice. BERT uses a masked language model objective. It randomly masks out some words and then tries to predict them.
Oh, so it's forced to infer the masked word based on the full surrounding context, both left and right, without actually seeing it.
Think of it like a fill-in-the-blank game. You see the sentence, "The blank sat on the mat." To fill cat, you need to look both left, the, and right, sat on the mat.
And because the transformer's self-attention already looks at the whole sequence, it's perfectly suited for this bidirectional task.
Exactly. The self-attention mechanism working in parallel naturally supports this bidirectional conditioning across all layers. This pre-training approach yields incredibly versatile models. The paper notes, the pre-trained BERT model can be fine-tuned with just one additional output layer.
So you get a powerful general-purpose language understanding model, and then you just add a small task-specific head on top?
Yes, without substantial task-specific architecture modifications. This made BERT incredibly efficient for adapting to many NLP problems.
The impact was immediate and profound. BERT achieved new state-of-the-art results on 11 natural language processing tasks.
That's an incredible breadth of improvement, from question answering to language inference, all building on this transformer foundation.
It pushed benchmarks like GLE score to 80.5%, 7.7% point absolute improvement, demonstrating its empirical power.
So the transformer's parallelizable attention gave us the architecture, and BERT showed how pre-training on vast, unlabeled text using bidirectional context could unlock its full potential for general language understanding.
Precisely. The transformer gave us the engine, and BERT developed the fuel and a powerful training strategy for it.
It really feels like the birth of an era. The transformer as the architectural spine, and models like BERT as its first truly widespread, impactful applications.
From a simple idea of attention is all you need, to a detailed mechanism of query key-value interactions, and then to a foundational model like BERT, we've seen how a single technical idea can reshape an entire field.
It really compounds. I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.